So in section 10.2, which is called regression, we're going to talk about the regression equation. And that is also called the line of best fit. And it's basically just if your data sits in a line and that line is strong, you know, that data has a strong correlation, then we're able to come up with a line of best fit, which allows us to predict other values in the line. So the regression equation looks like this. So notice this is a y hat, and that's, simply because if you're given sample data, then it's not the population line of all the data, it's just for the data that you have. This should take you back to the days of y equals mx plus b, if that sounds familiar. In this case, the way it's written with what I just underlined there is more like this. But if you take yourself back to those days, you should remember that the value in front of the x is the slope, and the value here for b is what's called the y-intercept. So if you were looking at a graph, it would be where your line crosses the y-axis. So again, this might be taking you back, but it's the same stuff in that way. So notice that it uses the term algebraically because it is algebra. So this is called the regression line, the line of best fit. You have your x, which is the explanatory variable, and y, which is your response variable, just like we talked about in the last section. So what this line does is if your data has a strong correlation, then this line gets as close as possible to as many points possible on your graph. So it is called the best fit line because it best fits the data points. It fits as many points as possible, as close as possible. Now, in this is how our book uses the notation. B1 is the slope of the line, so how it's increasing or how it's decreasing. And B0, so that's what it means to have that little zero there, is the y-intercept. It's specifically the y value of the y-intercept. Now there are formulas to find the slope and the y-intercept, but our focus will be on just using the calculator to give us those values. So you can see that you can find the slope by using the correlation coefficient, your r star, as well as the standard deviation of the x values and the standard deviation of the y values. The y-intercept can come from finding the mean of the x values, the mean of the y values, and then using that slope. But again, that's not going to be our focus, but just know that they do come from somewhere. Round off rule for the slope and the y-intercept is 3 significant digits, and that's because it could be a decimal, it could be a whole number, and so by going 3 significant digits, you're going to kind of have enough values to be kind of legitimate. So let's take a look at an example here. Notice that I have it written slightly different so that I could fit everything on one page, but everything is there. We have 5 patients at a hospital and the information regarding their height and weight. So notice this is the scatter plot. You have the height, those are considered the x values, and then you have their weight, and those are the y values. And then the idea here is, do those points look like they are approximately in a line? And hopefully you would say, yeah, those points look like they are in a line. That line is a positive correlation because as the height increases, the weight increases. You would say they do look kind of, like they are in a line, so linear, which is the only kind we do. And since they do look like they are pretty close together heading in that same direction, we're going to say a strong correlation. That's what we would make an assumption on just visually. For B, it says find the correlation coefficient test statistic, determine whether a correlation exists. So what you can do now if you want is you can pause it and you can put the x and the y's, the x's here in one list and the y's here in one list, and see if you can get the correct r star. So So I'm just gonna, I don't have a lot of space, so I'm just gonna do like a little mini version of a hypothesis test here. And so we're not given anything, so I'm gonna do alpha being 0.05 because I don't have anything, I'm not given anything. R star, again, if you put in the x and you put in the y's, you should get 0.903. So you can see that's a pretty strong correlation in the positive direction, heading up. If you look in your table, so thinking about our table from the last section, if you look in the table, you should get that R, so that's, we only have 5 data points there. So n equals 5, alpha is 0.05, and it looks like if you look in the table for that value, you're going to get 0.878. And something I do want to mention is the less values of n you have, the stronger that R needs to be. And that makes sense because there's more room for error if you have less values, and so you're going to need a stronger coefficient, correlation coefficient. So here we have our 903. So our 903 does sit to the right of that critical value, that R, and I can also just remind you that it could have been a negative correlation too, so we do want to think about where it sits on either end, but it's a positive one, and so we can see, yeah, that's a pretty strong, our R star is strong, so we are going to have the idea of rejecting H naught. Again, I'm just doing a very truncated version here, but we do have the sufficient sample evidence to support a linear correlation. So determine whether a correlation can exists. So we would say there is sufficient sample evidence to support a significant linear relationship, and then that is between, and it kind of makes sense, between height and weight. Height and weight. Okay, so mini version, I don't have the H naught and the H1 there, but again, I'm just with my space. Okay, so then it says find the line of best fit and sketch it below. All right, so now this is where our calculator comes in. So you should have your values in 2 lists, and you want to make sure you know which list you have them in. I've got all sorts of lists all over the place here right now, and I'm going to double check my numbers. We only have 5, so make sure that everything corresponds X to Y there. Okay. Okay. All right. So then what we do is, this is just going to come from the calculator. This is going to come from the calculator. So I'm going to go to tests, and I'm going to go up to the LinReg t-test again. So the same thing from section 10.1. And then I'm going to put in my lists. So where I put my 2 values. So I put them in 5 and 6 because I have a lot of stuff in there. So I'm going to put in list 5, and then I'm going to put in list 6. And then we want to remember that we're always doing the not equal to for this. And we press calculate. And we get a lot of stuff. And one thing I want you to notice is that in your calculator, it says y equals a plus bx. So because of that, that basically tells you what value you get for a in your calculator and what value you get for b have to sit there. So I look, and it shows me, just by looking down, that my a is going to be a negative 359.8. Okay. But remember, we want 3 significant figures, so I'm actually going to round that to negative 360. So negative 360, because the 8's going to make the 9 round up, so that becomes a 0 and the 5 becomes a 6. Now for the b value, again, right in the calculator, you can see it's 7.7 0.75 to 3 significant figures. So all I need to do now is just put those values. So my y hat, the line of best fit for this sample data, is going to be negative 360 plus 7.75x. And then it also says to sketch it below. Now I wouldn't really expect a student at this point to like know how to like sketch that line, but all that they're really asking right here is that somebody just, you know, get an idea of, I actually cannot really do this with anything but freehand, just to draw a line that is as close as possible to as many of the points as possible. And it should be a straight line, so do not maybe focus so much on my line, but the idea there is the line of best fit gets as close to as many points as possible. And so you just do the best you can with that in your notes. So the last thing that we do is interpret the slope. And what you really want to remember here is that slope is the change in y over the change in x. So if it's taking you back to your algebra days, that can also be thought of as rise over run. So that should take you way back. For us, that is 7.75, because our slope is 7.75, and as long as that is a number, we can put it over 1, because that's how to make it a fraction. But that's what allows us to see that the top is the change in y, and we know that y is our weight values in pounds. So it's pounds, and then down here the x value, the change in x, is in inches. So I'm going to put this, and specifically I have 1, so that's 1 inch. So what this tells us is for every, and I'm going to start with x, for every inch increase in height, there is a 7.75 pound increase in weight. And the big idea with this is this would allow someone to, say, predict somebody who's maybe 80 inches tall, or somebody that's 71 inches tall. How much would we expect them or predict them to weigh? Because their height and weight should follow approximately along that line. And that's one of the big ideas with regression, is the idea of being able to predict. So the interpretation of slope is what I just did, which is for every unit increase in the explanatory variable, which is x, on average, there is an decrease of slope, which is just your y, units on the response variable. So you're typically going to see a slope like 0.5 over 1, or like we just saw 7.75 over 1, or you might even see something enormous like 467 over 1. But the idea is the top is always the y, that's always this idea, and the x is always the 1, which is the unit increase, 1 unit increase. So that's how to think about that, and we'll look at more in a little bit. Now the y-intercept is sometimes in a real-world applicable situation, like it's not really real-world applicable to have a y-intercept, but it visually is just where you would cross the y-axis, which is what happens when the x value is 0. So the explanatory variable is x, and then the response variable then becomes, in the context of the book, if you remember, it's this, the way the book writes it, and so this b naught is your y-intercept. And then on the calculator, we're still just using the Lin-Reg t-test. So besides being able to give us our R star, our test statistic for the correlation coefficient test on linear correlation or not, it also gives us the values that we need for the line of best fit as well.